So hello and welcome to Bella Italia, to Bella Vicenza. We are here at our second SUSFERT seminar. SUSFERT is a research and innovation project, 5 years in the running, and innovation eventually has to come to a close and move towards commercialization. So today we'll be focusing on some of the results, some of the impacts that we have been striving to achieve. And we'll be looking at how the various components that we looked at a couple months ago in another seminar, which is viewable on our website, can and has changed into concrete outcomes, results, and in some cases, even products. So I'm delighted to have a panel discussion at the end of a number of high-profile presentations. And just a little bit of housekeeping, please do get involved. It's an interactive seminar, so please pose the questions on the chat. We will aim to answer these either after the various presentations or at least in the panel discussion that follows those. So let me kind of briefly go into SUSFERT. I assume most of you are familiar with the project and our activities. So myself, I'm Mikael Müge. I represent RTDS. We are the coordinating partner of a consortium of 12 companies, research organizations, and industry. Together over the past 5 years, we've been looking at solutions that would decrease the dependency on mined phosphorus up to 40%, thereby strengthening the circular economy, valorizing waste and byproducts, and also looking at improving water holding capacities throughout the system. We've demonstrated a lot of these solutions in products, also looking at controlled and slow nutrient release. And the aim was really to bundle these various components and solutions together to demonstrate innovative green technologies, all in an economic and feasible package of solutions. So we go into presentation time. One thing I like to do is to have a short demonstration of some of the capacities that we'll be presenting. So these are part of our fertilizer solutions. We call them part of a SUSFERT, which we demonstrate and present. So these are lignosulfonate-based solutions. We'll hear more about the benefits of these, but keep your eye on this as we go through the presentations. So we've just added some water into this NutriGel solution of SUSFERT, and we'll look at the implications and the effects of this throughout the next 2 hours. So without further ado, I'd like to hand over to our first distinguished speaker and actually the host of this facility here. He's Adriano Altissimo. He's the founder and CEO of Landlab. So we've been conducting a number of field trials with Landlab. So Adriano has really begun, he's an expert in biostimulants. He began his research in the early 2000s, and since then he's really focused his attention on new ways of agriculture based on precision nutrition and plant protection on the bio economy, particularly on biostimulation. So Adriano, welcome. Thank you very much.
Thank you.
And the floor is yours.
Yes. So thank you for being here today. I have to say the Burgmeister is not here, heute, but he told me, please tell to the people they are very welcome. So you are very welcome in this Palladio villa, so which is built in the 15th century and still operating as a municipality house. So that's a special location you asked for, and then you are here.
Correct.
So biostimulant as a driving factor. This was for bio-based fertilizer. So this connection between the these two elements was stimulating my imagination. So, and then I went to this subject that you gave me to talk about. So at the end, there are two main drivers. So the bio-based fertilizer and the biostimulant. How do we use them? For which purposes, for which goals? Shortly, you know all that what the biostimulants are. So are products that are designed for impacting the plant's physiology, the nutrients availability in the soil, the microbiome, and bypass harsh conditions like abiotic stress and so on. And it's a market with a forecast of growth in the coming years, very significant all over the world. So where are the biostimulants in the picture of the let's say tools for agriculture? There are a kind of bridge between organic, organomineral, and plant protection. We have to say that because often we see effects which are not directly related to the disease control, but they are because the plants are in a better condition. The law is not facing this subject. The law is dividing clearly all the things, but in fact, biostimulants, scientifically speaking, are in the gray zone. A plant with a better health is a plant that copes better also with the diseases, clearly. So it's a very broad landscape, as you can see. Amino acids, humic substances, nitrogen fixings. It's really a mix and mess of products that are now getting available in the market with a sparkling industrial and research activity. Let's keep. Just, I would like to point the attention to some slides to tell you where this movement started. So starting in the early 2000s, and you see as a number of scientific publications in the last 20 years, is not a linear growth, is a very strong growth in the last years. So meaning that the science went ahead industry, but now science is really supporting innovation strongly. I took the freedom to look to the condition of biostimulants in different, so we have plant extracts, which is roughly just 7% of the market today. Bacteria, fungi, yeast is maybe 20% of the biostimulant market, and still more than 70% is by humic acid, fulvic acid, protein hydrolysate, so amino acids, and seaweed. So that's the main market, what we call the commodity biostimulant, not the special biostimulant, but the commodity. Bio-based fertilizers are a very wide, and I would say also wide environment. So there are so many product streams coming to agriculture that sometimes it's very difficult to separate them. So just an example. So one of your targets is to improve the phosphorus efficiency. Good. So this is an example of the difference generated by low soluble P and high soluble P. I will bring back this slide later to explain why. So the difference is very significant. This was on potato. Another key factor is those are fertilizers. On the left, you have rock phosphate, which are allowed for organic farming. On the right, you have a TSP, which is not allowed for organic farming. So organic farming, for instance, is suffering a lot by this low availability of phosphorus. The same is for nitrogen fertilizer, organic. You can see this is a curve generated by our phenotyping platform. So we measure the plant height, and you see how 7 different organic fertilizers here are giving completely different 7 growth curves. So all of them are equal in terms of nitrogen applied, but the plant performances are totally different. Below you have the untreated, and above you have the fastest one. So nitrogen is not, nitrogen title is not per se a guarantee of performances. So some effect here, for example, we have 2 organic phosphate sources and several humic acids types and doses. So you can see that only one, I don't have a pointer here, I know, it's not working here. Okay, only one, you see AJ there. Okay, now. It's there, I don't see. Yeah, good. Only that one is able to push up the availability of phosphorus above the untreated level. The other types and levels are not able to do that. Meaning that in this case, we have a biostimulant which is boosting the availability of phosphorus above the rock phosphate level. So it doesn't mean that It doesn't mean that biostimulants per se, they have an efficacy. We did many tests with the different products. For example, by looking to the available P at the end of the experiment. This is another interesting effect we found. By using special, in this case, plant extracts, by using special products, we were able to increase the P available at the end of the experiment, meaning that we were able to catch P out from the unsoluble fraction in the soil pool and put in the soluble solution for the plants. Other trials are showing the same effect. So more phosphorus available at the end of experiment, meaning there is more phosphorus available for the plants. So you have some questions. Yeah. So, effect on the microbiome. This was a question coming yesterday from several people. We did see, for example, how some products were able to increase the colonization of native mycorrhiza. So not the new mycorrhiza, but the native mycorrhiza to the plants, demonstrated by this trial with this microscope analysis. But we went deeper, for example, by looking to the bacteria, abundance of bacteria in the soil during after the experiment. And we saw that some products were significantly able to increase the bacteria copies in the soil, meaning that the system was really boosted by the application. We went even more deeper, you can go, and then we went into the nitrogen cycle involved bacteria by counting the specific functional enzymes in the soil, and which are related to the nitrogen cycle, and we observed that some types of biostimulants can enhance the bacteria which are activating, for example, the nitrogen, the ammonia oxidation to nitrate, meaning make more available nitrate for the plant's uptake. So those are all data science that say some biostimulant can enhance the efficiency of the cropping system. So it's not just a simple yield, but there are reasons behind. And then a good product has to be supported by good reasons behind. This slide is a summary of more than 36 trials run all over Europe in the last year. The zero is the control for every trial. And you see that out of 36 trials, we got 33 positive on the phosphorus use efficiency by the precise use of a very specific biostimulants. So on completely different crops in different regions, from Sicily to Finland, from potato to tomato, whatsoever. That's to prove the robustness of a product. This type of activity are needed. Otherwise, the communication and the data are too weak and cannot be spread around with sufficient confidence by the end users, by the farmers. So this is an example on how can, by the way, this was a result of a European project also on phosphorus use efficiency. So then if we couple with your goal, it's even more interesting to see that there are many possibilities to enhance the system. So at the end of the story, how shall we use this product? So we have a cropping system with different physiological phase. Then we have to increase, for example, the nutrient use efficiency, but we have several critical events like drought, heat wave, frost, or UV. And we have plants that we suppose are in comfort, but maybe they are not in comfort because we can control some factors and other we cannot control. So when do we use that? The key factor to me to enhance the efficiency of the crops is to deal with these elements. So we have to know the weaknesses of the cropping system in the season, depending on the crop, location, soil, climate condition, and so on. We have to know precisely how the bio-based fertilizers are working. when the nutrients are released during the season, if they are released in a sufficient speed, or they are too slow, too early, too late, according also to climatic conditions. And we have to know very well the biostimulants to apply in a very precise moment, because those are not products that can be used in any moment of the crop cycle, but they have to respond to specific tasks, to specific claims, when they can make their job. So at the end, set a precise plan according to external conditions, which are the driver of the plant's growth. So the conditions are the drivers, the products are the support. Both things have to be put together and applied, used in the right way. So at the end, we can have a nice portfolio of solutions which combined together really are able to enhance the cropping system efficiency. So this is our conclusions of the activity we are running. And then I would like to share with you, because it's giving another level of integration, another level of research, another level of investment needed to better understand and use these possibilities we are generating. This is the last one. Yes.
Thank you very much, Adriano. It's very interesting to see how these biostimulants can influence fertilizers, agriculture. We'll be looking now specifically at the importance and the impact of bio-based fertilizers. So here, it might still be a niche. We're looking at bringing the niche to the norm. And for this, we will be joined by Leo Fock, who is the CEO of Coterra Holland. And Coterra Holland is a market leader in the production of organic fertilizers. And in his role, also, Leon is the chairman of EUROFEMA, the European Organic Fertilizer Manufacturers Association. So welcome, Leon, and thank you for joining us. And then you just feel free to click yourself through.
Okay, thank you very much for the invite. And for the question you asked me, will organic fertilizers or bio-based fertilizers develop from niche to norm? To start with that, what is an organic fertilizer? Because I don't think you can answer this in general. And I'll try to find a few axes how we could assess if this development from niche to norm is realistic or not. And I have one problem: there are no data in Europe available on all these categories. So a lot of educated guesses today. That's one. Very quick on EUROFEMA, European Organic Fertilizer Manufacturers Association. That is an association of associations, so of European countries associations, representing other associations in Brussels. We were actually founded in Venice, so just a short while from here in 2007. And we had one goal: we wanted European legislation for organically based fertilizers, which we almost have, but it took 15 plus years. We have Bel from Belgium, Unifarm from France, IFAG from Germany, BMA from Holland. We have FOMA from Spain in there. So I'll look at this question from a few axes, from a category point of view, because you cannot put bio-based fertilizers in one bin. So there's a lot of different products in there. From a supply side, so where are those raw materials coming from? Who wants those fertilizers? Can the industry cope with this movement from niche to norm? And I'll try to wrap that up and show the impact by category of markets. Let's get with organic fertilizer. I'll do a quick categorization. So we have unprocessed organic materials, basically manure, for example. They are bio-based fertilizers. They work very well, and they are used a lot. Unprocessed from farm to field, huge amount. Actually, very good fertilizers. Then we get to the process single source fertilizer. So if you process a manure by sterilizing it or drying it, you start making a fertilizer product, and you can keep it, you can ship it, you can sell it. So it starts to become a product from a single source. For example, a dried process digest could be a single source. The next group is the NPK fertilizer. So then we start making products, mixing several raw materials into an NPK plus fertilizer, 777 or something like that. And the next group is adding something to it, making those fertilizers more efficient. And we call it more complex NPK biobased fertilizers. So if we put something out of the last presentation to a processed NPK fertilizer and use it on the right crop in the right timing, I just learned, then we have the perfect fertilizer for the industry. On the right, you see the classification used by the European Statistical Institute or something like that. They try to validate data on that classification, which is totally useless in our case. So don't look there. Okay, we have these categories. Where do they get their raw materials from? And here we see a classic issue, a classic approach. If we have an organic material, we first want to eat it, and so we use it as food. Then if we can't eat it ourselves, we'll feed it to our animals. First we feed it to production animals, even if that's not possible, we feed it to our pets. And if we can't feed it, we used to say we use it as a fertilizer. But the last few years, we got a new category which came in there, which is very bad for some of our businesses. That's called energy. So we now start to make biogas and burn wood and do all types of stuff with actually perfect material for fertilizers. But in current market situations, those three categories bring more money to the table than a fertilizer in general. So the organic business has quite some high competition on the organic matters they need to make fertilizers. So if you ask me from a supply side, from niche to norm, okay, if we have a lot of sun energy and wind energy and we stop with all the biogas systems, we might have room to grow. But if I look at current raw material markets, which are already niche, they are already divided amongst those who need it. From a supply side point of view, I'm not pessimistic about the market though, so don't get me wrong. Let's look at the demand side, from niche to norm where. So we have mainstream agriculture. And what do we do in mainstream agriculture? We use as much unprocessed organic biobase as allowed. And then if we need more, we use mineral fertilizer. Very sound strategy, brought us a lot of well-doing in the world, feeds a lot of mass. Then we of course have the market of organic agriculture. And the choice there is very easy. You can't use mineral fertilizers. So you use circular processes as close around your production site. And then if you need the fertilizer, you need an organic fertilizer. So if you ask me, what is a market where niche to norm is already there, it's organic agriculture. That's not because they want it, but that's because of regulation. So it's a very regulatory driven market. Then we have special agriculture and horticulture. So now we get into the expensive crops and flowers and greenhouse growing. And that's a market where interesting things start to happen. If I take, for example, crops that are sold in supermarkets, some want to have those organic, and then you can say, okay, we add an organic fertilizer. Ornamental is everything which looks nice and you put into your garden. We have landscaping and turf, so that is everything where you play golf on and football and where you walk through in the park. And we have the hobby markets. If we would look at value, so how much could you charge per ton to make it very easy, go from below to above. So hobby market, if you buy a box of rose fertilizer in a garden center, that costs you $7.95 per kilo, so that's 7,000 euro something per ton, which is a lot more than you can ask for an unprocessed manure, where you probably get 18 euros a ton. So there's a wide range between those markets. So demand side, always try to look for which market are we talking about. Then our industry, we are small, medium enterprises. More small, some medium, but that's the market. We did estimate about the volume they can produce today, and that's in the hundreds of thousands of tons, but not in the millions of tons. So if you want to make that from niche to a norm, the industry would need a large scale. So let's given we solve this supply side issue, you basically need to build a lot of factories in Europe, or large factories. And who will put in the money? So there's a question mark, how fast can the industry adopt? And it's not a question of converting a mineral fertilizer factory into an organic fertilizer. So there are low capacities relative to the total market of fertilization. They're quite diverse. They act local in general. So we have these pop and mom shops that make an organic fertilizer and sell in the region. And then, of course, we have impact of FPR in the industry. The industry was really it couldn't really grow fast because it was very difficult, and it's still very difficult, to sell an organic fertilizer from one European country to another. And try to sell, somebody from Spain here in the audience? No, so I can talk about that. Try to sell an organic fertilizer in Spain from Germany, it will take you 5 years to get it in, if you're lucky. But FPR will change that, so we'll make the business case better to increase the size of the industry. Because the market is growing now, so it's becoming a single market, so it makes more sense to invest in the industry. So now we look at supply side, demand side. So yes, there's supply, but it could be an issue. Yes, we have demand that differs per market. No, we don't have the industry size yet, but there is industry, and FPR is opening the market and changing the business case. So I'll try to wrap that up. Will a bio-based fertilizer become a norm for the fertilizer products? And okay, let's put a time scale in there within the next 10 years. I'm very bad at forecasting the next year, but let's take next year. So will it become norm for agriculture? Unprocessed, yes, it already is, but processed organic fertilizer, I don't expect. And the current strategy of using soil improvers, which are unprocessed, and controlling your crop with mineral fertilizers is very effective. And we will get rid of some of the problems of leaching of nutrients. Organic fertilizers, organic agriculture, of course, yes, because no choice. Like in horticulture and ornamental, there are some markets where people will like to have a plant in their garden which never saw any chemical in its life. So yes, in ornamental you will find some of those organic fertilizers, and sometimes even from an agriculture point of view, they help to improve your soil. So it helps. Landscaping and turf, moving very fast at markets. If you go to Barcelona and the stadium is called Camp Nou, they have a very green stadium and it's very green managed, so they use organic fertilizers there. Lots of golf places in Europe, they want to manage their golf place in a green way, so they use organic or organically based fertilizer. So it will be mainstream for those markets. And let's say in the hobby market, that discussion has been gone. That's a no-brainer. And we even get the legislation in some countries in Europe to ban the mineral fertilizers. So for the next 10 years, from niche to norm, in some markets, yes, it will be hard to keep it the pace. My last time, and I'm in time, I think. So we have no real data, sorry for that, because there's only one statistical number for this whole group. 3101000. So we have no subdivision in that. Using unprocessed organic material locally is, of course, still the first best choice. We don't put energy in there. supply side will not adapt to, yes, fast growing demand side. So we see that demand side, but we have this competition with energy. So demand will most probably exceed supply. So the answer to the question said at the beginning, yes, for some markets, some situations, but not for all mainstream fertilizers. Thank you.
Thank you very much, Leon. So encouraging thoughts, still a number of challenges and obstacles to overcome. And we hope to be part of the solution going forward together. So thank you very much. We'll see you back on the panel. So Leon is, like Adriano, part of our advisory board at SUSFERT. We're looking at these larger pictures, policy pictures, and looking at ways to move forward to indeed turn the organic fertilizer market from niche to norm. We go into a more specific issue now, and that is the nature of iron supply and the importance of that for fertilizers. And so we've been looking in the framework of SUSFERT at a number of issues, including phosphorus and also iron. And so I am delighted to have on the table next to me here, Lucas Branta, who's he's a biotechnologist from Agrana Research. He's been looking at a number of solutions moving forward in terms of innovation. He's joined by Rüdiger Weichesmüller from Agrana Starch. So Rüdiger is responsible for fertilizers at Agrana and is a product manager and key account manager for the fertilizer division. So they'll be guiding us through the significance of iron supply for fertilizers. Lucas, the floor is yours.
Thank you, Mike. Well, let me give you a short introduction into the iron supply as an added value bio-based fertilizer. Well, to begin, iron is an essential component for plants. It is a cofactor for a lot of enzymes and also used for cytochrome production and chlorophyll production. You can see very well in the pictures there that with iron deficiency, there is less chlorophyll in the leaves of this grape vine. Well, where is iron deficiency the most common? It's in Mediterranean countries with a lot of lime in the soil, which makes the pH over 7. And therefore, the iron is bound as insoluble iron oxide. Furthermore, the bicarbonates affects the iron uptake with the same effect that it alkalizes the soil, or it buffers the soil to a pH a little bit over 7, and therefore hinders the iron uptake of the plants. Well, what does the plant do, and what can the farmer do? The farmer can, for example, ventilate the soil and expel the CO2 by plowing it, and therefore reducing the buffering effect of the bicarbonates. Or he can use artificial iron supply in the form of EDTA. In essence, it's like a sequestrine 138. What can the plant do? What does the plant do in nature? It decreases the pH around its root network with the by expulsion of organic acids or siderophores. There are some specific plants which can do that very well. And what has to do with bio-based fertilizer? Well, iron is an essential element of life. And bio-based fertilizers are made out of these organic substances, therefore have a natural iron content, even if it's only in trace amounts. The availability for plants, therefore, depends mostly on the raw material and the soil environments, be it the microbiome or the pH of the soil around it. And well, as a good example for bio-based fertilizer, which has no problems in inhibiting the iron chlorosis, we have biogenazole by us.
thank you for the invitation and the introduction. Let's go in detail for the product biogenazole, which is produced by Agrana. Biogenazole itself is an organic fertilizer. It's fully plant-based, so free from animal components. It is certified for organic agriculture in several markets in Europe. It is produced by Agrana Starch in Austria, in Bischofsdorf, where we have our bioethanol plant. So Agrana is mixing several byproducts from their plants, like from the bioethanol plant, the DDGS, the so-called the DDGS, the dried distillers grains soluble, which is based on wheat and corn, and also some other liquid products, for example, the residual molasses from the sugar beet factory, the potato nitrogen concentrate, and the cornstarch liquor for our potato and cornstarch factories. We are mixing these products wet and drying them together and achieving some granules and materials. The nutrient composition from biogenazole is about 5.5% nitrogen, 2.5% phosphorus, and 1.5% potassium, with at least 90% organic substance. It has also a natural iron content, which origins from the raw materials and is available for the plants. We have several existing markets like Austria, Germany, Italy, Spain, Greece, the Netherlands, Poland, where we have also our distributors and partners. And we are also having some markets which are under development at the moment, like France and Bulgaria, Hungary, for example. The main areas of application are vegetable cultivation for cash crops like spinach, cabbage, also fruit and berry cultivation, for example, apples and viticulture, salt and substrate for the fine material to achieve a bit more of organic matter into fertilizers and also into salts, herbs, sugar beets, and sports green areas, for example, for soccer, we are at the FC Sevilla and also in Austria for the Lask Linz. The benefits of these products are to promote humus development and soil health. Biogenazole also has a fast initial effect, so the mineralization curve from the nitrogen is also rapid, increasingly, and also have a long-lasting effect for the next 2 or 3 years. It has also an adequate nutrient supply. It is already effective at low temperatures, which is, for example, necessary for cultivating spinach in February. It has a pleasant odor, so it is a not stinky fertilizer. It is organic and fully vegan. No danger of over-fertilization, harmless for humans and animals. And also we have measured in several trials the last years no nitrogen leachate. And it is preventive against iron sclerosis, which are be shown by the results of the trials throughout the project SUSFERT. We did several trials throughout the project SUSFERT in viticulture and fruits, for example, orange and kiwi in Italy. The trials were done with the University of Natural Resources and Life Sciences, the FOCU in Turin or Vienna, and also with Landlab here in Italy. We did this trial several years in glasshouse and field trials. And for example, you can see on the right side of this presentation slide, 2 pictures. We were mixing for a trial with viticulture, the soil with approximately 30% of calcium carbonate. And on the picture on the above, you can see the roots from the viticulture trial with mineral fertilizer, and on the below, the roots from the trial with biogenazole. So we achieved every year vigorous plants and also a great root growth. Also, the yields were every time comparable to mineral fertilizer, and iron sclerosis could not be detected over the years and many more. So if you are interested into our fertilizer product biogenazole, and if you have another questions, do not hesitate to contact me. Thank you.
Thank you very much, Rüdiger. So always exciting to see some of the products that are commercial and how they then go through various improvements and tests and validations within the framework of projects. One of the things that we've looked at on top of the iron chelating capacity is the soil improvement initiatives and capacities. And for this, I'm delighted to welcome back to our second seminar, Renate Weiss from the BOKU. So the BOKU, she works for the Institute of Environmental Biotechnology at BOKU. BOKU is the University of Natural Resources and Life Sciences in Vienna. You're a senior scientist working there and has been leading the development of our lignosulfonate coatings. And on top of that, you have pioneered some of the new applications with regards to soil improvers. Thank you, Renate. The floor is yours.
Thank you, Mike. So today I will present the soil improver applications that are possible, and one of the variants that we provided in the SUSFERT project. So for this, first of all, we need to know what is a soil improver. And there is actually a definition in the European fertilizer regulation that states what soil improver is. This is in PHC 3. And there is a distinction between organic soil improvers and inorganic soil improvers. And for the organic soil improvers, the material has to consist 95% of solely biological origin. And it can be out of peat, leonardite, lignite, or it's not allowed to be of any other material that is fossilized or embedded in geological formations. And you have to have more than 20% dry matter. And of course, a very important point are the contaminants. You have to stick to certain limits that you can have, so you need a lot of the testing for your product. And then an inorganic soil improver, it's quite nice because it's any other soil improver that is not an organic soil improver. And of course, you have again the limitations on contaminants and heavy metals, copper, like this. So then all the definitions are quite nice. So, but what are actual soil improvers? And soil improver is an organic material substrate that improves the condition, fertility, and structure of the soil. And there are actually a lot of forms of soil improvers that are suitable for these applications. For example, some organic ones are, as you all know, a compost, but also tree bark, manure, seaweed, molasses, or worm casts. And for the inorganic ones, limestone, rock dust, gypsum, polysaccharides, and polyacrylamides. So, but what is now the difference between a soil improver, a fertilizer, and compost? How do we discern this? So this a soil improver versus a fertilizer. The soil improver can add macro and micronutrients via the organic matter. And it is improving the soil fertility, but also the structure. It can also be used to change the soil pH. And this is something we should keep in mind for later. And as a difference, inorganic fertilizers usually only provide the macronutrients, so N, P, and K, and sometimes also magnesium that are needed for plant growth, but usually they do not have a positive effect on the soil structure. And then soil improver versus compost. So actually compost is a soil improver because it will release macro and micronutrients over time. And also, in addition, you can add other soil improver ingredients to improve it further. And how do they work now? So a soil improver is destined or is meant to provide ideal conditions for the soil system to flourish and that the soil gets healthier. And this happens due to the symbiotic relationships between the root system and the fungi and also the other microorganisms like worms, nematodes, bacteria. So this is something very important. The soil improver should not interact negatively with this system. Also, a soil improver facilitates the easier absorption of macro and micronutrients. And if they contain biochar, perlite or vermiculite or other small stones, they actually usually help aerate the soil, again having an improved soil structure. And also if they contain biochar or hydrogels, they can actually retain water, and this is very positive to decrease soil irrigation and plant irrigation. So now to some examples. One of the examples is agrobiochar, which is a novel soil improver. This is a lignin-based hydrogel, and it has the potential to reduce the soil water input and improve the irrigation efficiency. And agrobiochar has been registered as a soil conditioner in Austria already, and it also obtained an organic certification. And in addition, they have CO2 negative balance, and they are very environmentally friendly. And this is also an output that we will show during the SUSFERT project with the LCAs that will be provided. So what is now the soil improver we developed during the SUSFERT project? This soil improver is based on marine calcium carbonate granules, which were coated with lignosulfonates and probiotics. And there we did a lot of in vitro testing to actually ensure that the polymerized lignosulfonates that are used for this coating to be non-toxic to plants. You can see here the results of one of these trials where we can show that the germination is not negatively affected by the lignosulfonate. And also during the growth, you cannot see or measure any negative effects if the lignosulfonate is applied to the system. Just to explain it a little bit better, in this trial, you actually do not add the soil improver as a finished product, but you test the lignosulfonate coating in an excess amount on the plants to test if it's toxic to the plants. And then we added the probiotics, so microorganism strains that are known to help the plant root system take up nutrients and heighten the nutrient availability in the soil. So therefore we tested different strains, and this was done on lawn. And through measuring the lawn cuttings, we could show the increase of the plant growth and the yield on the lawn cuttings, especially with the strains AB53 and AB25. So therefore, we chose these two strains to go into further testing in field trials. And first we went into field trials, or again in lawn, where we could show the effectiveness by seeing the better structure of the root system when the microorganism, the probiotic, is in the system. Also the lawns are much stronger, and they can resist adverse weather conditions like droughts much better with the soil improver. In addition, we have the calcium carbonate in this soil improver. This means it has an effect on the soil pH, especially good for very acidic soils, which can be found in many regions in Europe, and which help improve the yields for other plants like potatoes, which we also did. Here I can show you some field trial results of the effectiveness of the soil improver in the potatoes, where we can see that we have overall higher yields and higher starch content in starch potatoes when the microorganisms are applied in the form of the soil improver. So here the soil improver acts together. This soil is very acidic, so we have the calcium carbonate base of the soil improver, and then the lignosulfonate coating, which has an effect on the release of the calcium carbonate, and then also the probiotics in the coating, which help the root structure to develop nicely. And this leads to higher yield and higher starch content. So if you want to know any more about the soil improvers we developed, don't hesitate to contact me.
Thank you very much, Renate. It's super to see some of these initiatives that are being put to test and to trial, and then actually see the effect and the yields on this. The next question de facto is, where do we take all this? Is there a next generation of NPK fertilizers? And to help us understand and answer that, we are joined by Sylvain Pluchon from Groupe Boyer. He's Director of R&D and agronomist, and he's been looking at a number of solutions for NPK, next generation industry advancements and innovations. And he was here with us remotely, but in heart and soul, to guide us through and see what is the next generation of NPK. Good morning and welcome, Sylvain.
Good morning, Mike. Hi.
The online seminar does not work without some technical hitches, and we are just incurring ours. Bear with us, Sylvain.
Okay, maybe I can start to quickly present to you Roulier Group and Timac Agro. Roulier Group is a group of...
Sylvain, please click through your slides.
My share my screen, or you manage that?
The one on the screen. Okay, I can click for you.
Right. Okay. Next slide. Okay, you can see here the main key figures about Roulier Group. Roulier Group is a French group. We have different businesses in different sectors. As you can see, we are working a lot on soil, plants, and animal nutrition. Of course, we sell and we produce by ourselves solid and liquid fertilizers, amendments, biostimulants in more than 100 countries. And actually, we have more than 7,000 people close to farmers every day, visiting close to 20,000 people, farmers per day. So we have close to the market and close to the technical expectations, needs, and so on. Okay. Just to complete what we have heard before, for our different industrial plants, I think it's very crucial to talk about that, how we can produce bio-based products, how we can supply. I think that Leon has clearly defined the different issues, how to use organic matter, how to process them, how to supply in quantity and in quality enough products to be able to fertilize enough hectares to have impact on the system. Next slide, please, Ben. Okay, you can see here the different location where we are settled. Of course, you can see in France, but also in South America, in all the countries in Europe and so on. So if we make a focus on Europe and the main topic for SUSFERT, regarding the P sources and how to find a way to increase or to decrease our dependency for non-European P sources, it was tricky. So was mainly concerned about Struvite, one of kind of recycled P sources. So next slide, Ben. Just some key figures for sure, how actually the way to fertilize crops are not efficient. Roughly, we can say that the nutrient use efficiency for nitrogen is close to 50, and for phosphorus close to 20. So it's not enough so it's not enough for sure. And of course, more and more it's topic to decrease our dependency for non-European pay sources. To add to that, you know, more and more, because we have pressure, social pressure, and positive pressure from policies, from regulations, and so on. We have to address soil quality or soil health, air quality, and water quality. And for each P and P losses is involved, and increase or decrease the quality of the system. So it's a key point to work at a bigger scale and to think about the 3 pillars: soil, air, water, for sure. Please, Ben. Okay, so what was our strategy altogether in SUSFERT, you know, is to permit or to allow more technical new or next fertilizers, for sure, based on bio-based product, you know, bio-based raw material. But as you can imagine, it's not because it's bio-based that it's more efficient, you know. If it's bio-based, it's great to decrease the dependency, but we have the target also to increase nutrients efficiency. How to do that? For sure, by less application per hectare. We have to permit that, to use TrueVite or other kind of recycled P. Maybe to dig better, to promote foraging, you know, to dig better P, endogenous P. Also, we have to address and to better use the synergy between the different nutrients, you know, N and P, K, or these efficiencies are cross-linking. So we have to work all together, and it's why it's what we have tried to do, and for sure, but careful. We have to increase microbial activities, but maybe to stabilize P or to dig better endogenous P. But careful, when we activate microbes, we have more microbial respiration. It's more CO2 in the air at the end, so it's less organic carbon in soil. So again, all is a cross-link, because we have to address also maybe carbon sequestration or organic carbon content in soil just at this stage. Ben, please. So, Ben, next slide, please. Okay, so what we can say after 3-4 years trials in field, for sure we can say that TrueVite is an effective way to replace a part of mineral P, mainly SSP, in our field trials. It was more effective, more sure if for localization of P, you know, through new formulation, macrogranules formulation. Microgranules is very little granules put in the row close to seeds, you know, and roughly the dosage is 25 kilograms per hectare. So in this case, for sure, it's a effective alternative to use TrueVite. We can assume that on maize and different crops, it's pretty well established, for sure. What we can say that if we combine the TrueVite with PSB, we have a slight effect, but positive effect for sure for PGP effect, and in mean, maybe we can stabilize close to between 0 to maybe 15, maybe 20 units per hectare. 20 could be maybe a bit high, but roughly 10 units per hectare could be well balanced, to say. Okay, we have to promote root foraging, as I said previously, and we have to well address a synergy or between N and P to increase in efficiencies of both in same product. Ben, please. So to conclude this slide and the next one, Next NPK for sure should be a rental friendly product for me, and for it will be pretty obliged. More technical. We have to. I think commodities and the quantity used is too high to replace quickly. It's not feasible, and Leon has probably well said that. So we have to address more technical things, more technical agronomical issue, and in a way, bio-based products, the wide family of bio-based products could be alternative and a good way to increase the global efficiency of the system. Okay, we can boost biological functions. Okay, Renate has mentioned the regulatory stuff. It's a key point. Okay, so bio-based products has more and more and better well defined and well. The regulatory framework is better for such products more and more, so it's great. But we have to be to talk carefully, you know, regarding the return of invest for farmers. You know, in mean bio-based products it's more expensive compared to commodities. So great, we have to work on alternatives, but you know, we have also to be able to reach economical products, you know, regarding what farmers can invest per hectare for sure. And next slide, and the last one, please. No, thank you.
Thank you very much, Sylvain. Do stick around for the panel discussion, which will follow after the next two presentations. There we are. Excellent. Thank you very much for that. The next presentation that we have planned for, it gives me great honor to welcome our SUSFERT's Green Rebel onto the stage. So you might remember that earlier this morning we used some what we have been developing Nutrigels with the lignosulfonate-based solutions and soak them up with water. Not sure if you can tell the exact difference here, but it's absorbed dramatically and have turned into gels. So the man in charge of these gels is Gibson Nyahongo. He's a co-inventor and founder of AgroBiogel that we have introduced and brought back as a spin-off from Boku into the project of SUSFERT. And he's here now to show us the Nutrigels in action. Gibson,
great,
go for it.
So thanks a lot. Yeah, my name is Gibson, and already been said and hinted out also, I'm the co-inventor of AgroBiogel, and I'm excited also to point out that we have here in the audience one of my long working partner, Professor Georg Gubis, also the co-inventor of AgroBiogel. And when I decided to leave the university and start AgroBiogel, I gave my head to Renate, who is also doing an excellent job continuing with these studies. So a little bit about, should I go? Good. So what is Nutrigel in action? First, we are a spin-off of the University of Natural Resources and Life Science Vienna, that is Boku, as AgroBiogel. So this was how we started the company. But we take AgroBiogel and Unfortunately, I cannot show you here, but I think this is enough. So from this to this, and we can even take more water with agrobiome. What is the whole idea of agrobiome? It is to increase the soil water holding capacity. What is the aim behind? The aim behind this, the farmers, this is now even to a 9-year-old, a 5-year-old, knows that water has become a scarce commodity worldwide. So that is the aim. If the farmer is cultivating, is using irrigation water, let's say he's irrigating 3-4 times a week, with agrobiome, they are able to reduce that irrigation maybe to 1 to 2 times in a week. In this way, they are not only saving water, they are saving associated costs, which is the labor cost, the irrigation, some run on electricity. So you are saving water in this regard. But more so also important with agrobiome is that increasing erratic rainfall patterns. I'm originally from Zimbabwe, Africa, and we drought, we have learned to live with drought. And I'm sure in Europe, you have not yet learned how to live with drought. So in where I'm coming from, Tune, I've been living there. June, July, there is always 3-4 weeks, there is no rain. And for sure, the farmer loses their yield. Now with agrobiome, if they put agrobiome, it will be able to store water, release its storage to the plants. That is the idea of agrobiome. But going further, agrobiome is the carrier. It mimics humus, degrades into humus. What does this mean? Humus in the soil is increasing soil organic matter. It is also, in this case, increasing microbial activity, availability of nutrients. It is a charged polymer, all important cations for the plant, nutrients for the plant can be naturally stored in agrobiome. That's the idea of agrobiome. Based on this, this is why in the project SUSFERT, we embarked on saying, this is our first generation of products based on agrobiome, where we are putting in nutrients into the agrobiome. But also, as you can see there, we can put agrochemicals, we can put herbicides, pesticides, we can make meds, we can make many other products out of agrobiome. We think this is the start of a new journey, using a resource that is abundant in Europe, that is locally available here, that is renewable, that is sustainable. Good. So in NutriGel, what have we done so far? I will run you through some highlights of what we have done here. We have put probiotics into agrobiome. We have put NPK. We have put bioadenosol and tried to see what happens. Are these things compatible? Can they really help with the plants? Good. The first experiment were with microorganisms. The idea is to solubilize phosphorus, make it available to the plants. I'm not an agriculturist, but our agriculturists, when they went there, when the plants had around 7-8 leaves, they could see the differences very well. Maybe from the picture you might not see it, but the most important thing, of course, this is what I always say. For us, we are happy when we have at least the same yield. And when we can increase it, it's a plus to us. That is, so here it was really clear, our agrobiome is helping the microorganism, providing the environment for the microorganism to solubilize the fertilizer. Here are deficient. This is what monitored or confirmed by looking at the iron deficient or phosphorus deficient. And I'm sure you can see here with bioconazole. So, okay, the highest deficiency is until 1, and the lowest deficiency going down. So we have bioconazole in the agrobiogel, then phosphorus, phosphorus agrobiogel microorganisms. There is some effect happening in terms of making first phosphorus available. And this is also confirmed by the height of the plants. The same happened with just taking the control as 0, and then there is the increase in the growth of the plants. So where there is agrobiogel plus, there is always a positive effect. One thing that happened, because agrobiogel, as we say, it increases soil water holding capacity. And it has been a question by many of our customers, what happens if my field is flooded? Will this not destroy my plants? And we could show, and unfortunately, at first we are, of course, we were not so happy because it happened. One, this experiment is very critical to us. And then we had a flood. But good, it turned out that that flood was very good to demonstrate that even when after there is a flood, when there is a flood, actually agrobiogel helps store the nutrients inside. So where the 3 of us are standing there in the middle, those were under flood, and you see the controls beside them, they're a bit shorter than that. This is, of course, the whole team was going to assess there. They wanted to convince them because we told them, no, agrobiology can do it. And we summoned the whole team to come and see. And they were taking notes. Good. This is, I'm not going to do the same. It's exactly the same experiment. We did it on 2 different fields and exactly the same results. So it's a reproducible in different geographical locations. We would expect, of course, today, maybe Simone will give us the updates on the studies they did here. But at least from the preliminary studies, it showed me again here, there was a trend that agrobiogel plus the fertilizers, there was something happening. You will confirm with the yields, I hope. But before that, I will show you also the yields from Spain. We ran the exactly same experiment in Spain. The only difference, Armeria, I'm sure everybody knows Armeria, is the vegetable garden of Europe. And there they dig trenches, dig out the soil, put sand, and then they grow the tomatoes. So they put agrobiogel into this extent. So as you can see here, maybe the first part, everything was regularly watered. We are not very much interested in that, but what is clear there, even it shows that agrobiogel, even when you are regularly watering, the plants are growing well. This is yield, right? There was increase in yield with agrobiogel as compared to the control. And now when we reduce the watering by 20%, then we just comparing the control with the highest yield, we have 40% increase in yield just with agrobiogel. What does this mean? We can go down with agrobiogel, as far as I can see, we can even go down to 50% and still get the same yield. So we are in this process of saying what is the optimum economic concentration of agrobiogel that we can give him, which is a good message that we got already. Also, I show you a bit of also this happens in fruit, pears, almonds, all this, we could show that with the agrobiogel has a positive effect on the growth of these young plants. Very clear difference. This is also forestry because we, as agrobiome, our raw material is wood. And to us, it is very critical that forestation is our priority. So reforestation, creating new forest is our focus because this is our raw material. So we are also doing a lot of reforestation. In Austria, we have planted more than 20,000 trees. And in Germany, we have also this active team who are really doing an excellent job in terms of reforestation. And this is, they could use agrobiology, they use also the synthetic ones, which are commonly, which have been on the market for over maybe 60 years or something like that. So, and again, agrobiology really works wonders. Great, I'm there. But in Austria, we also have, we are really interested in this, and the same thing we could show after a year, pull out the plant, and we still see agrobiology very active around the roots. So this was pulled after a year, and then you would see really agrobiology is still very active. Good, I think generally the observation that we have from now is agrobiology, we can use it as a carrier of nutrients, NPK, or any other, we think this is compatible even with many other untested products that can be used to support plant growth. Good, thanks.
Thank you very much, Gibson. Very exciting developments there. And as we could see, maybe I can, we have a number of SUS kits, these prototypes that we have modeled, and some of these are turning into products as we develop some of the final analysis. The project is still running until the end of the year, so by then we will have a handful of products that will be pursued further towards commercialization. You can read all about the SUS kits, as we call them, on our website. One of the things that we saw in the last presentation is a number of field trials, the difficulties of holding, managing, and pulling results out of them. Thank God in SUSFERT we have Sebastian Michi, who manages our field trials. So it's been a challenge throughout the project and almost throughout every year, as the extremities of drought and rain and floods become increasingly unpredictable. So I welcome Sebastian. Sebastian is a senior scientist at the Institute of Environmental Biotechnology at POCO, and he focuses, apart from the field trials in SUSFERT, on the use of artificial intelligence in plant breeding. Very exciting stuff. Now back to the basics and making sure that we get the most out of field trials. Here's Sebastian to guide us through some of the challenges that are involved with managing field trials.
Thank you very much for the introduction. So yeah, let's talk about field trials. So first of all, why are field trials important? So yeah, field trials are really a crucial tool for product development and testing new technologies in agriculture, such as these prototypes we developed, for example, in the SUSFERT project. And field trials here enable researchers and also scientists to evaluate new products and assess their performance in real life conditions. And of course, field trials also generate a vast amount of data from various sources. Let's say nutrient analysis. In yield trials, of course, you have let's say grain yield, biomass yield, things like this. And well, these are very important for decision making afterwards. And of course, you also got to store this data somewhere, so this can also be a challenge sometimes. And of course, these field trials also facilitate the transfer of knowledge and best practices, basically from research institutions to the farming community in the end. So that's what we are hoping for. And but of course, we also facing some challenges in field trials. First of all, of course, we got to define an experimental layout and follow good experimental practice. We got to randomize our trials, replicate everything, probably also test everything in a lot of locations. stuff like this. To get the maximum amount of information, with limited resources, that means money, because field trials are also very important, as we learned also during the SUSFERT project. And despite all these efforts, giving good experimental layouts and good experimental practice, still we are facing a lot of, let's say, varying weather patterns we cannot really influence. And well, this of course can make it sometimes difficult to draw conclusive results from, let's say, a single year's season or single season. Of course, sometimes we also have the challenge to find appropriate locations with, let's say, desired soil properties, nutrient content, pH, and texture. For example, in SUSFERT, we conducted these phosphorus trials, so we needed this P-deficient, phosphorus-deficient locations, which are not so abundant in Europe. So this has also been a slight challenge, but we managed it in the end. And of course, afterwards, we also got to conduct a statistical analysis for drawing meaningful conclusions, and also effectively communicate our findings. We have publications, for example, or science to public, for example, using mixed linear models. And then in the end, of course, we like to, in the ideal case, scale up our findings to commercial agriculture operations for a real world implementation. Well, and when it comes to SUSFERT, we would like to prove there that in our field trials that these novel fertilizer products with reduced mineral P are as effective as conventional fertilizers. And first of all, we did set up some protocols, and harmonized protocols, especially because we tested our material in a lot of countries and with a lot of different service providers. So we had to make sure everybody did the same thing. And there we tested basically our most promising SUSFERT products and combinations against benchmarks from the market. These trials means actually. This combination means we had these, obviously the struvite, which were already presented now a bit, and then we wanted to combine them with the probiotics to make the phosphorus also better available to the plants, and this lignin we used as a coating for a slow release of these nutrients, to make them longer available to the plants. And in our trials, we also monitored a bit the P dynamics in our field trials, basically by a spatial temporal assessment of various agronomic traits. That means that basically we just harvested, we worked here with maize, and we harvested these plots at different time points and assessed basically a lot of different traits like nutrient contents and obviously also the biomass. I'd just like to present very briefly a major outcome of these trials. First of all, we got, as said, we got to find these optimal trial sites, and we found them in France, Germany, and Austria. But as already mentioned, these extreme environmental influences like drought or flooding pose always an element of uncertainty. So we mitigated basically this risk of trait failure, but first of all, by replicated testing in these multiple locations within each country. But still, you can see basically here, we had this benchmark of a single superphosphate, and we wanted to see a very nice dose response curve. And here, this is basically expressed always relative to an unfertilized control, and then 20 kilograms of SSP, 40 kilograms and 60 kilograms of SSP. Of course, with an increased P fertilizer, we would also see a higher dry weight, but sometimes this was not the case due to this unforeseen or environmental influences. For example, in this trial here, there was no response at all, or some erratic response, but still in some of these trials, at least, were lucky. They worked out very well. But yeah, as you can see, P trials are very challenging. Just about 30% of them really worked out nicely. And conducting a meta-analysis of these trials, which worked out nicely, see what the basic outcome was there, that our SUSFERT products, in comparison to this single superphosphate benchmark, showed an average performance which was similar to normal business as usual single superphosphate fertilization in terms of biomass. Also, if we combine this with these probiotics and lignin coating. And just imagine now, there was some indication that this struvite shows a huge, larger variation in performance if you apply this in different locations. So we had to also look at it, which is, and this was true. So if you look at the average performance across all these locations, the variation was larger than using this benchmark from the market. But if we combine this with our other SUSFERT products, with these probiotics and the lignosulfonate coating, we could reduce this variation a bit, make it similar to the benchmark of the market. And this basically means it's a very promising result, and also what we would like to see, that our novel SUSFERT fertilizer products with reduced mineral P can be as effective as conventional fertilizers. And with that, I'd like to thank you for your attention.
Thank you very much, Sebastian. So this brings us to our last speaker, and there is no project without an LCA, and we have the best. So I welcome aboard this table here. Next to me, Mark Spieler. So Mark Spieler is a postdoctoral researcher at the University of Antwerp with a focus on resource recovery from wastewater, phosphorus and nitrogen. So he's been assessing all our initiatives and products or prototypes. And actually over the last few days, we've defined some of these prototypes to become real products. And so information on those will follow imminently. But he's here now to guide us through some of the procedures, processes, and results from our life cycles. Thank you, Mark.
Indeed. Thanks a lot for the introduction. So we had this already. It's about the life cycle assessment of multifunctional fertilizers that we produce here in SUSFERT. I will also repeat to you what we mean by multifunctionality of fertilizers and which aspects these are. That's right here. So this includes the slow release properties, the coatings that we have that we've seen also in the previous presentations, the biostimulant, what I will call probiotics in the following, and the agrobiogels that, for instance, increase the water holding capacity that you have also seen by Gibson, and of course the struvites and the siderophores that we also have touched upon. These are, when we combine all of those, we get our various kits, our different products, our 6 products, and I will look in the following at the individual products together, their individual impacts that they have on the environment. I will mainly look at CO2 or exclusively look at CO2 emissions, CO2 equivalent emissions, although LCAs are of course much broader than this, including different impact categories. But that would maybe lead too far today, so we'll make it relatively simple for you to follow. So indeed here it is already stated, the objective is to evaluate the environmental impact of these multifunctional fertilizers, and the question whether these fertilizers reduce impacts compared to conventional market alternatives, and today only the CO2. A little bit of how the following results will be looking like. So on the left-hand side, you see our innovations, the multifunctional fertilizers that we are having, and on the right-hand side, here, this picture should signify the conventional alternatives like an SSP, for instance. So as we are producing our novel SUSFERT innovative fertilizers, we're of course replacing coatings, replacing other biostimulants, or SSP, for instance, in trials, and this is then an avoided product, hence this nicely crossed out X here. To then calculate CO2 emission impact, we need to apply a simplified calculation as you see down here. We arrive at the net impact, at the balanced impact of the SUSFERT innovation minus the business as usual, the BAU, as you will see in the following slides, which is basically the cross that you see here on top. So there's a little bit of context for you to follow the following results and interpret alongside with me what you're going to see. And that's a little bit looking like this. So we start with the coatings and their respective environmental impact. So here on the top right corner, you see the calculation that's carried out that I just explained. And here, first time you see this graphic now, you see like a very simplified bar chart. What do you see in this bar chart? You see the 0 points, which is the important one, because everything up with a positive sign means it has an impact. So this blue bar is the lignosulfonates coating using glycerol. In this case, as a plasticizer, and they have an impact here, just in relative terms as percentage. I'm not going into the exact CO2 emissions that will be part of this. You see that here, so upwards means an impact, they emit CO2, but as we replace polyethylene, so coatings, alternative coatings are some sorts of plastics, different types of polyethylene, or also some oils that are hydrocarbon-based could be used as coatings, but we avoid those coatings in the process. And so we get, strangely enough, a negative impact. Of course, we are avoiding something, so we can subtract this here as shown up here. So we balance these two impacts and we get then this little dash, the net impact, which is negative, which is actually good. We could make a smiley here. So the conclusion, the first one you can see from this presentation here, is that the lignosulfonates have a negative impact when you produce them 1 kilo of them as compared to 1 kilogram of polyurethane. And that is about 1.5 kilograms CO2 saved per kilogram of these lignosulfonates produced. If you then want to know more specifically where are these impacts coming from in this very dark blue bar, so informing, for instance, SAPI, who's producing these coatings, how can they improve their processes? We can drill into these processes and we can see that, for instance, the plasticizers make a sizable impact here, that electricity plays a role, but also the enzyme that is used in the process plays a role in generating this impact. So SAPI can then go ahead and optimize together with us, finding alternative energy supplies, finding alternative plasticizers, and determining the best, least impactful compositions of their process. We did the same for the probiotics. As I said in the beginning, we took a slightly different approach here for the probiotics. We asked the question, how much probiotics or how much phosphorus fertilizer would need to be saved to achieve zero burden in terms of CO2 approach for production of probiotics. And the answer is firstly in the left-hand slide. So you see the dried probiotics have 100% impact on top. And if we save 9.28 kilograms of phosphate rock, then we have a zero CO2 emissions balance. And that equates to about 3% savings of P demand when you take a 90 kilogram P2O5 application in a conventional maize field. And then we can ask further the question, probiotics, well, where are those impacts coming from? And you see that in the processing, in the fermentation process, they're using the electricity plays a role, natural gas plays a role to sanitize the reactor, to clean it basically, and also glucose as a feedstock plays a role. So we can again see whether we can change the feedstock and further reduce the impact. This is a substantial impact here, although whether we could recover energy in some way. The agrobiogels, this amazing agrobiogels, nothing happens. So what's their impact? And these agrobiogels are, in our assessment, as amazing as they are here today, because they have an amazing property. They can save you irrigation water application. And if you were to irrigate your crops, this has a large impact, of course, in terms of pumping, in terms of abstraction of the water. That has also impacts in other categories of LCAs. But our results show, if we take conventional irrigation in Austria of maize fields, that we can really reduce our CO2 emissions quite a lot by this negative bar signified here, almost 500 kilograms CO2 equivalent ton dry matter of lignosulfonates. But also to Gibson, he can further improve his process by, for instance, improving his electricity demand and reducing this further, or using renewable electricity, or reducing his gas consumption. Chemicals play a smaller role in this process. Struvite, we assessed also the struvite that's sourced from wastewater installations, for instance, as we have seen it before. Also struvite, we see a similar pattern as in all our previous partial products. We see that this dot here is on the negative side. We can avoid more than 100% of the impact. That means the negative bar is twice this red bar going up. How do we save these impacts? How do we generate a negative impact in this case? Well, some of this impact is derived from avoiding the production of single superphosphates. That needs also CO2, of course, but also a large part is the avoidance of iron free chloride in the wastewater treatment itself. And in this wastewater treatment, iron is used as a precipitant for phosphorus that is dissolved in the wastewater. So for the wastewater companies, struvite production is actually a way of removing phosphorus from the effluent and therefore meeting environmental norms. So, but they can save this, and this brings us here to savings. But also struvite production itself, the precipitation of struvite in the reactor can be further improved to do, and here electricity plays a role, but also the base dosage can be further improved potentially. In some cases, there's no base dose, in fact, when you produce struvites, but also the magnesium chloride or sulfate that is necessary to provide the magnesium ions can be further improved potentially. Then we look at the siderophores. Also here you see the negative impact. How is this coming from? The siderophores are functionally equivalent to EDTAs. We are working on improving the exact equivalence, but if we were to replace EDTAs, we can see that we can also avoid, again, CO2 emissions. The bar is negative and our dash is in the -60% area. So also here we can save significant amounts of CO2, and we can further improve the process of producing siderophores by ASIAs, for instance, by improving electricity demand. If we further upscale, this will naturally be happening. Naturally not, but it's usually the case when you upscale, you get more efficient. Glucose, the feedstock, doesn't play such a big role in our impact. So focus should here be on electricity. Finally, we can combine our products together in these different mixing ratios and formulation ratios that we are using here. On the left-hand side, we see one of our SUS kits, that is the combination of struvite, lignosulfonate, and probiotics. And here we see that especially the struvite plays a large role in avoiding impacts. Here you see it then in actually CO2 equivalents. So more than 3 kilograms of CO2 can be avoided per kilogram of our fertilizer produced. And we also see that the lignosulfonates play a small role, while the probiotics, the way they are modeled at the moment, that's not shown here because we modeled the net 0 point. So we avoid CO2 emissions here. The same applies to another SUS kit, which is composed of agrobiogels and probiotics. Also here, we mainly due to the agrobiogels, we've seen their magnificent impact earlier. We can avoid about 2.5 kilograms of CO2 per kilogram of product. So that is quite good. And yeah, here's also the assumption for the probiotics. So overall, our fertilizers, well, that's my next slide. Overall, our fertilizers that we produce in these compositions that I just shown you, they avoid CO2 emissions. They are not just CO2 neutral, but indeed they are reducing CO2 emissions when compared to the current market alternatives. And I think a very important takeaway is also to work on electric energy to improve further our electric energy consumption. We are contributing with this project also to the agenda of electrifying our economy further and going away from fossil fuels. And as our process has shown, lots of impacts and lots of use comes from electricity. We first of all electrify it, but we have potential to further reduce this by using renewable energies, for instance. And with that, I would like to thank you and close here.
Thank you very much indeed, Mark. We are slightly behind schedule, but I'd like to still ask some of our presenters and speakers to join us here on the panel. If I can ask Leon to join us, and Adriano, if you could be so kind, to come up, and we've got a few questions that have come in, which I'd like to address, also in the light of what we've just heard. And Sylvain is joining us remotely. So the first, if you maybe get the yeah, wonderful. So the first question I have is actually to Adriano, and please everybody feel free to engage here. When we look at how the biostimulants contribute to the overall sustainability, we've just heard in terms of the LCA that the biostimulants have to be as efficient as a reduction of 3% of peat. So when we look at this and combining this with bio-based fertilizers, is this achievable today, or what do we need to do to demonstrate this better?
Well, I get it. With the product, the solutions available today, the goal of enhancing the household efficiency is achievable, clearly. So, but I'd say my presentation, the key is to precisely define how to use the tool. So if I go back to the presentation of Mr. I don't know the name from Rouillet,
right?
Technical products, that's exactly what I mean. Solutions that need a far more precise application methodologies. Therefore, industry and science have to be closer to the farmers. Because the farmers are using the solutions which are use and forget. This is not the case anymore.
Well, perhaps that's a question to you, Sylvain, also. When you were speaking about the need of NPK and fertilizers to become more technical, and if we look at that, technical means also more complex in communicating and understanding. What initiatives do you think need to be taken? And maybe it's also a question to Leon, to train the farmers to not only kind of understand, to make this niche to norm accelerated in terms of understanding, in terms of making a very complex technical item simple to implement, to use, and to understand, to be communicated.
Yes, I think there are problems with mineral fertilizer. You know exactly what happens if you put 10 kilos of eggs on the land. And with organic fertilizer, you don't know. Because the mode of action is different. It depends on soil life, it depends on temperature, it depends on crop, it depends on region. So where we need to go is to make it easy for farmers. Let's say you have this crop and today this is the temperature, and probably we need more real-time information on the site where you are, and combine that into, again, easy to use, spread it out how much application fertilizer.
So how does Group Rouillet deal with this complexity of communicating these innovations that you're working on?
My point of view that we have to choose our targets, our issues. We can just say that bio-based it's a global target, We have to clearly define the main agronomical challenge, where the situation and where the bio-based products have a crucial advantage and big impact compared to commodities. You know, we where the physical and chemical properties of soil are limiting a lot the P use efficiency. We have some cases where the water eutrophication is the key point. We have some location where the organic matter is very, we have too much organic matter, so how to use that differently. But definitely, I think that we have to address dedicated and specific purposes, and not just to say that bio-based it's enough as target. So I'm sure that even if it's recycled, we could use such noble recycled raw materials with the same less efficiencies compared to mineral raw materials. So we have to avoid that. If we use noble raw materials or raw organic materials or recycled sources, we have to use them with carefully, you know, very carefully, dedicate on specific community issues. So it's my main purposes, and I'm sure that in this case, such projects could give a big advantage, permitting to have a global return of investment, included positive environmental effects, beneficial benefits, and so on. So if not, it will be just quantities, how much, price, and return investments as usual. So, and in this case, I think it's not a short-term topic.
It's for sure a complex issue that we're addressing here. I'd like to kind of take the focus on the future. We talked about a little bit of the hurdles, challenges, and limitations that we're facing today. Maybe we can look at two aspects, maybe the challenges and the barriers that exist to a widespread adoption of biostimulants. And as we heard from Leon earlier, that while demand probably will outstrip supply in terms of bio-based fertilizers, and I'd like to understand how would the biostimulants kind of perhaps aid or strengthen the case for bio-based fertilizers in mainstream agriculture?
Okay, so we have two things. I think we have a release of nutrients, so when we release, and we have use of nutrients, so losing use efficiency. And I think biostimulants could help on both of these actors. So could we steer release to the moment we need it, and could we improve the nutrient use at that moment with biostimulants? Which would mean that we need less kilos of fertilizer. But we need Landlab to find out what to do when.
I'm glad we're here. Adriano?
Yeah, that's the key, because as I told Leon said a few minutes ago, I mean, first I would repeat myself. Know your bio-based very well. Know the kinetic, the dynamic of nutrients availability, because that's the crucial factor. And follow during the season, because that's, if you know that, then you can support the plant nutrient uptake. If you don't know that, you are in the dark. Biostimulants can target both the soil system and the plant per se. Can act in different aspects, can move, can upregulate the transporters, for example, of the nutrients, therefore make the nutrients movement faster from the roots to the leaf. Can enhance the nitrogen fixation of the nitrification processes. It can be positive or even negative, because if it's too much, then you're leaky. If it's too slow, you have less uptake. So these specifications are crucial. The information, this know-how is crucial to precisely use both tools in the right way. But it's possible, it's realistic. There are systems to understand in real time how is the temperature, water going, and therefore, and the plant's phenotyping, how it's going, and therefore you understand in which phase are your crops, and then you can forecast your applications.
I like when you say, you know, being in the dark, you know, if we go from the dark to the light, Mark, what role would the LCA play in identifying these areas of improvement? Because we, of course, it's the sanity check of everything that we do here. How can this be used for future improvements?
Yeah, so we are looking mainly at the production of these fertilizers. I think Landlab is looking at the efficiency of their application, and we do the same, but further upstream in the production process, we are looking at the efficiency of production and to further minimize in the production process the impacts across various impact categories. And what's typically done is using a hotspot analysis, as I've also shown, to show the places in a process where you can make maybe easy gains, but in the first instance where the major impacts come from, and then work with the partners of the projects or future projects to see whether alternative products, alternative ingredients could be used, like alternative energy sources, like alternative feedstocks, whether ethanol or glucose or something like that. We could then assess their respective impacts in various impact categories, and by that further reduce the environmental impact and not just shift the burden of impact from one to the other, from an improved fertilizer to somewhere else upstream in the supply chain. So we're taking the supply chain view and trying to make better, improve the process from an environmental point of view.
I see that we're closing in on the final minutes of our seminar. I'd like to pose the final question, which is double-barreled to each one of you. So I'd like to understand kind of in terms of your fields and areas and bio-based fertilizer, biostimulants, where will we be in 5 or 10 years? And if you had one wish to make that 5 or 10 years rosier, what would that be?
So this will be a much more adoption of bio-based fertilizers across the board. And my wish would be that we can somehow bring all the knowledge and all the data there is in an easy way to use. Because everything we discussed today, don't ask an average greenkeeper or farmer to follow that. So we need to be very modern today. We need this artificial intelligence that supports our users, bringing all the knowledge together.
Yeah, well, we will for sure in the near future, it's already happening, be more and more, have the farmers more and more adopting this solution. That's the fact. Also because in the agriculture, there is a lot of me too. What is my neighbor doing? Why is doing that? I also that. So this, direct communication is also working in the market. The same, my wish is to, and not only my wish, our wish, it's also we are working for that, is to integrate industries. Because only in the integration between fertilizer producers, biostimulant producers, biocontrol producers, you can really enhance the efficiency of the crop. Otherwise, everybody is selling a simple solution. And then, so that to me, a change in the industrial mentality has to happen. And from that point, farmers can really profit to a combination of a portfolio, a diet, I would say, for the crop. That's the next frontier.
It's a little awkward question,
No,
but I think you have an answer for it.
I have an answer. It's not about the answer, but I was very intrigued by the presentation of Leon. So I think the challenge for bio-based fertilizers, organic fertilizers in general in the future will be to find a way that we are not trading one evil for the other. We are looking at byproducts that are somewhere coming free in a complex system in our economy. And as we have seen with first generation biofuels, we are not just wanting to shift the burden from now utilizing the waste stream that has been used for feed, for food, or energy crops, and shifting it away from there and causing then problems in another sector, be it the energy or the food supply sector. We need to find bio-based fertilizers and organic fertilizers need to find their niche and need to show that we can divert these waste streams, these byproducts, and make better use of them than other alternative uses, then maybe an energy use. Is it better to use it as a fertilizer or to digest it and produce biogas? These questions need to be answered, and they can be answered through an LCA approach. For instance, to say, yeah, let's not shift our byproducts to digestion, but make it a fertilizer, improve our food chain, etc. And that, I think, will be the real challenge, because in our economy, all byproducts are virtually used, and there are very few that are still exploitable. And when there are some, we need to find those and further exploit. The struvite is a good example. So far, struvite has not been, or the iron phosphate sludge has not been utilized in agriculture in many cases. But here, struvite is really tapping into a new resource of phosphorus. And there we can increase our potential. So we need to find those. And if we don't find them, we need to avoid a shifting of the burden in our economy.
Thank you. And then I guess it's my last wish, and where I see this going in 5 or 10 years. So my wish is really for continued funding into the research and innovation for these initiatives. SUSFERT has come a long way to demonstrate that there's a number of feasible solutions that will make a direct impact on society, on technology developments, on industry. So more of these researchers and initiatives are more than welcome. The other wish I have, de facto behind that, is that you keep following us on social. Tune in. We're actually presenting at the EU Industry Days in Malaga next week in front of the European Commission, some of our findings and initiatives to foster more dialogue and provide more opportunities for other initiatives and activities. So the other good news I have to share is that there will be an extensive conference on the final results and findings, outcomes, prototypes leading to products later in the year. Sign up to our newsletter, you'll get the feed, check us out online, stay up to date, and hope to see you soon again. Thank you so much to our speakers and panel and for the viewers, and stay safe and see you next time. Goodbye.